In the world of infectious diseases, HIV has been one of the toughest hurdles to clear. HIV has been a big focus of public health research since the 1980s, and we still do not have an official cure. Well, we have cured a handful of people, 7 to be exact. And while that's a win, it's worth asking, why only 7? Why not 7 million? We have awesome treatments that have saved countless lives, but it would have been even more awesome if, instead of needing to take medication every day for the rest of your life, we could have a cure that gets rid of HIV for good. Scientists are working hard to make that dream a reality. Here's what's been making it so hard that they've only pulled it off 7 times, and how that could change. We have no universal cure for HIV, but that's not for lack of trying. It just happens to be an especially tricky virus to get a handle on. For one thing, HIV mostly attacks the T cells of your immune system, which are, ironically, supposed to be the ones that fight your body's intruders. HIV takes down your defenses at the source. But one of the main reasons it's so persistent is that HIV is a retrovirus. That means that when HIV enters the body, it sticks its own DNA inside your DNA and makes itself an unwelcome, permanent guest. This patch of HIV DNA is called the latent reservoir because it's a pool of DNA that can hang out quietly without expressing itself for a long time. But as long as those instructions exist inside your cells, more of the virus can be made. So a lot of the research for a cure is focusing on trying to get rid of the latent reservoir. This is not an easy task. HIV is a master of stealth, keeping super quiet and leaving behind tons of misdirecting breadcrumbs. Even though many T cells that face off with HIV will end up with some HIV DNA inside them, only about 1% of those T cells carry a functional latent reservoir. Unfortunately, that 1% is still enough that people living with HIV have to take their medications for life. If you stop, the latent reservoir can wake up and start making HIV again. Except some people have been able to stop because they've been cured. As of filming this in 2024, the current count is 7 people cured of HIV. If you're watching this in the future and that number has changed, leave us a comment and let us know where we're at now. Now, these 7 are very special cases, and we're not yet at a place where we can say that we have a reproducible cure for everyone. For starters, all 7 people were treated with a stem cell transplant to treat their various forms of blood cancer, which can show up more often in people living with HIV. But curing their HIV wasn't the only or even the primary goal. And as far as cancer treatments go, this was kind of a last resort. Stem cell transplants are super risky, so it's not a safe candidate to recommend as the first line of treatment for anyone. This transplant involves basically wiping out your whole immune system and replacing it with a new one. The stem cells that become your immune system, including your T cells, live in your bone marrow. Your bone marrow makes blood, so swapping it out with new stuff is also how you want to treat blood cancer. It's just that wiping out all your T cells has the incredibly convenient side effect of, theoretically, eliminating the HIV reservoir. Since we have other very safe and effective treatments for HIV, putting someone without cancer through that unnecessary tough medical procedure goes against a doctor's golden rule of do no harm. Not only that, but even if we did want to perform this transplant on everyone, it would be really tough to pull off. First of all, finding a transplant donor is already difficult in general. You need to find someone whose immune system is compatible with yours, and not even your own family members are guaranteed to be a match. Secondly, for a while, it's been thought that the donor cells needed to have a super specific gene mutation for this to even work in the first place. And not just one, but 2 copies of it. This mutation is in the CCR5 gene, which usually codes for a molecule on the surface of T cells that HIV uses to break in. Having 2 copies of this mutation breaks all of your CCR5 receptors, but that doesn't really seem to be a problem, and it prevents HIV from being able to sneak in anywhere. But this mutation is super rare. Only about 1% of certain populations at best has the needed 2 copies. So considering all that has to go into a successful donor match and transplant, it's a miracle that we've been able to cure anyone at all. But that's not where the miracle ends. The 7th patient cured of HIV was officially announced in July of 2024, and because they've chosen to remain anonymous, we'll refer to them as the next Berlin patient. They are the next one because the first person cured of HIV was already called the Berlin patient, so now this person is the next one. The cured patients are named after where they were treated. It's kind of a thing. Anyone cured of HIV is already a justifiable cause for excitement. But what sets the next Berlin patient apart is the stem cells that they received. Instead of having 2 copies of the CCR5 mutation, the patient's transplant donor only had 1 copy. This means that even though they did have some CCR5 receptors vulnerable to HIV, the patient was still able to be cured. This is huge for increasing the pool of potential cure donors. And even though having just 1 copy of the mutation is still quite rare, maxing out at 16% of the population in the region studied, that is 16 times more than 1%. Yay math. But the next Berlin patient wasn't the first time someone had been cured of HIV without 2 of those elusive CCR5 mutations. A prior patient had been cured without any copies. Known as the Geneva patient, I told you, it's a thing. One person was somehow able to keep their HIV at bay without needing the CCR5 mutation. Of course, this is a super special case because other people who had the same stem cell transplant as them weren't able to get the same results in the long term. In fact, people didn't even think that this transplant would work as an HIV cure. They just needed to treat the Geneva patient's blood cancer, and they couldn't find a matching stem cell donor that had the double CCR5 mutation. But again, all of this is still very much up in the air, especially since several people living with HIV have failed to show the same results after a non-mutated stem cell transplant. So scientists are trying to figure out why the Geneva patient and the next Berlin patient were able to be cured with only 1 copy of the mutation, or even none.
Thanks to Brilliant for supporting this SciShow video. In just minutes a day, Brilliant helps you build real knowledge consistently throughout your busy week, and it's good for you. Learning a little every day can help with your personal and professional growth. If you want to make a daily habit of adding more learning to your life, but have trouble following through with that goal because SciShow only releases new videos 5 days a week, Brilliant has you covered. They literally have thousands of lessons to choose from, so when it's time to ditch the mindless scrolling, Brilliant is here for you. Find it at brilliant.org/scishow, the QR code or the link in the description. That link gives you 20% off an annual premium Brilliant subscription, and you'll get your first 30 days for free.
Interestingly, some of these cures were able to happen without needing to completely get rid of the HIV latent reservoirs. Although for some people, leaving behind even the tiniest bit of latent reservoir led to the virus coming back, cures have happened where the HIV DNA is just left in a state where it can't make any working virus. So, in a search for a reservoir reducer that isn't as invasive as a stem cell transplant, scientists are turning to the DNA snipping rockstar CRISPR-Cas9. CRISPR-Cas9 is used as a gene editing technology, and it was first discovered as a naturally occurring system in bacteria. Bacteria use it as their own version of an immune system, with the CRISPR-Cas9 system snipping up any viral DNA that tries to invade. This system is made up of an enzyme that can slice and dice DNA and a bit of genetic information to tell the enzyme what sequence to cut. Once the DNA gets snipped, scientists can either insert some new information to add a function to the cell, or they can insert some junk DNA to mess up whatever the gene was originally doing. You probably see where this is going. Why not rewrite CCR5 to the mutated version so HIV can't get in? If you can't make your own mutations, lab-grown is fine. Then we wouldn't have to put people through a stem cell overhaul to get that CCR5 mutation. A group of researchers from the US and China did actually try this out, and it worked. Kinda. They were able to use CRISPR-Cas9 to cause the mutation in a lab-specific line of human cells, but they weren't able to translate those results into cells collected directly from donors. So there's a lot more work to be done before we can start thinking about trying it in real people. One of the main concerns with CRISPR-Cas9 is the chance of accidentally snipping some of your DNA that isn't the target gene. If the CRISPR directions aren't specific enough, it's possible to accidentally make make a real mess of your genome. Scientists have ways of minimizing this risk as much as possible, but we'll definitely need a lot of safety testing to make sure we aren't cutting out anything important. As another approach, instead of cutting and pasting genes manually, we could take advantage of our immune system's natural cell-killing abilities. Substances called latency reversal agents are able to activate any latent reservoirs that are hiding out and force the HIV DNA to show itself. These agents include compounds that can force the HIV genes to be expressed as proteins, basically kicking them out of hiding. Some can amp up gene expression for some of the less expressed parts of the genome, which is where viral reservoirs tend to be located. Others smoke out HIV by increasing viral gene expression regardless of where it's integrated. Then the cells that reveal their stash of HIV DNA can get deleted by the immune system or other medications. Hopefully, by eliminating all of the cells with a latent reservoir, we can get rid of any chance of the HIV being able to come back as an unwelcome surprise. The challenge with this method is trying to get a latency reversal agent that works well enough to stimulate the immune system without causing any unwanted side effects. Part of the issue is also that we aren't really sure exactly why the HIV latent reservoir is so good at being latent. So it's difficult to know precisely how to reverse it. So far, there hasn't been much luck translating the concept of latency reversal agents into reality, but it's still an option that scientists think is worth exploring. There's been a lot of work done on our quest for a cure for HIV. While the virus has a few sneaky ways of trying to stick around in our bodies, we're working on staying one step ahead. Cure methods like stem cell transplants have had a few incredible successes in the past, but they're too risky and inconsistent to work for everyone just yet. Patients like the next Berlin patient give us hope for unexpected paths to a cure, and biotechnology like CRISPR-Cas9 and latency reversal agents give us new ways to get there. With HIV research making strides every day, we can look forward to going from a cure for 7 people into a cure for everyone.